Okay, meeting is being recorded. So this is lecture 3, part 1. Now we're going to start looking at specific signals that are very, very important. Two of them are discrete time, or forget about the time convention here. Two of them that are really important are impulse functions, impulse systems, impulse signals, and then unit step functions. Okay, so what is a unit impulse? So think about it something like this: nothing happens. I clap my hand, there's a signal, and then nothing happens again. So at a certain time, let's say for example of simplicity, at time equals 0, something happened. I clap my hand, so you have a boom, you have an impulse, right? Boom, just like this. Someone shot a gun or something, or yeah, you're fighting in a fight, nothing happens, and then boom, you get knocked out. That's an impulse function. Okay, this is what it is. In signals terms, though, let's come back to real signals. You have nothing happening. This is discrete. Of course, this is a discrete example. You have nothing happening. Boom, something happens. Okay, and then nothing happens again. So this is the definition of the impulse function. So delta n is equal to 1 when n is equal to 0. So at time t equals 0, you have an impulse. For other times, there is no impulse. So at other time n non-zero, you have your delta function non-existent. Your impulse function is non-existent. Okay? Now, a unit step function. A unit step function is nothing happens. And at 0, it shoots up to 1 and it stays at 1 forever. That's all it is. So nothing happens. And at 0, your function shoots up to 1 and it stays for 1 forever. This is, again, remember, and this is for discrete time. Okay? So here's what we have. We have this going on here. U of n equal to 0 for n less than 0, and is equal to 1 for n greater or equal to 0. So that's pretty simple and pretty self-explanatory. Okay, now there's a relationship between the delta function and the unit step function, and we're going to prove that graphically. So this is a relationship here. Delta function, why am I saying delta function? Impulse function. It's important to use the right terms. Impulse function equals to unit step minus unit step shifted by 1 to the right, or unit step delayed by 1. All right. So what do I mean? If this is my unit step, nothing happens, and at 0 you have 1. The delayed version is going to be the same thing, shifted to the right by 1 step. Okay, so you have nothing happens until 1 this time, and then your function shoots up to 1. Now, if you take this one and you subtract this one, well, zeros, these ones, they're just going to be zeros. 1 minus 0 is going to be 1, and then here you have 1, and here you have 1, and 1 minus 1 is going to be 0. So you see how the delta function is just the unit step function minus unit step function shifted by 1. Okay, and now the unit step function, it starts at 0, right? So you can say that the unit step function is the summation of infinitely shifted delta functions. What do I mean by this? Is if you have a delta function here, okay, that's 1, okay? But if you had a second one here, you have delta and minus 1. So you take the first, and then you shift it by 1, and now you have a second one. If you shift it by 2, you have a third one. If you shift it by 3, you have a fourth one, and so on and so forth, infinitely, right? And if you take the sum of all of them, well, you're going to get the unit step function, okay? That's all you're going to get. This is what this equation tells you. Now, you might be thinking you're not doing 1 plus 1 plus 1 plus 1. No, you have the sum of k equal to 0 to infinity of delta n minus k, which is equal to delta. Oh, let me give you some more room here. So we have sum k equals 0, infinity delta n minus k, and then this is equal to delta n plus delta n minus 1 plus delta n n minus 2, and so on and so forth. So you have delta 0 plus delta n minus 1 plus delta n minus 2. So you can see that this is at 0, and then this is shifted at 1, and this is shifted at 3. So you're creating that unit step function. So you have a delta, and you shift it, pop. Delta shifted, pop. And then you have your unit step function, which is just delta, boom. Shift delta, 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 shift delta, boom, shift delta, boom. And then you have 1. That's your unit step function, okay? Now, important property to notice here is if you have a certain signal and you multiply it by the delta function, it's going to be equal to the function at 0 times the delta function. What do I mean by this? Let's say you have some signal like this. Some arbitrary signal here. This is your signal. This is x of n, okay? And then you have delta function right here, okay? I'm going to do it big star. That's your delta function. Well, and then this is 0. Well, your delta function only exists at the point 0. You have a 1 here. So your function value, whatever it is, x of n, let's say it's x of n at that point, okay, times 1 is going to be x at 0, all right? This is x at 0, right? Your function is x of n, but when you set n equal to 0, you get that point, okay? And your delta function is only alive when n is equal to 0. So you have x of 0 times 1, and that is going to be your point. What happens here? What about the other points? Well, your delta function is 0 every single point over here. So you have 0 times your signal, which is 0, 0 times your signal, which is 0. The delta function is only alive at 0, so your signal will only be alive at 0. Okay? It's a very important concept to understand. Okay? Now, let's say your delta function is not alive at 0. You can't see my pen. Can you see now? Okay. Okay. Let's see your delta function is not only alive at 0. Now you're shifted by n naught. Okay? So you take your delta function, you're shifted by n naught. Now you can imagine if your delta function only existed at n naught in this case, before, your delta function only existed at 0. Now if you shifted by n naught, your delta function only exists at n naught. So wherever you don't have n naught, your delta function is 0. So your signal multiplied by 0 everywhere except n naught, your signal's gone. So the only place you're going to have a signal existing is at n naught. So that's why you have an n naught here. Okay, that's the more general equation. So go back, understand this real quick, and then move on. Continuous time unit step, and this is just switching up for discrete time and then continuous time here. So your unit step is 0 for t less than equal to 0, less than 0, and then it's 1 for t greater than equal to 0. Okay, greater than or equal to 0. I don't know why I wrote a 1 here. This is a big mistake. It has to be 0. Okay, I think I meant to say it's equal to 1 here and then did a typo there. But as you watch in the previous video, those are all mine. So, I write them before I record. So you have this. This is your unit step function. At 0, you have a jump to 1 and then stays at 1 there. Okay? And your delta function, you can write it as a derivative of the difference of the unit step function. Okay? So you have your impulse function is equal to du dt. And this, you can do some research as to what that is important. I don't think for the sake of this course you need to really understand that deep into it. So you can just take this definition as it is and then go from there. So if you integrate, or I should rather say, if you take this dt and you multiply on both sides, you have dut, which is equal to impulse dt. And if you integrate on both sides, you get the unit step function, which is unit step is equal to dut, and then integral of of impulse t dt. So that's your equation for the unit step function. So the sampling property for the continuous time unit impulse is the same thing, okay? Whatever we saw here, the same principle applies here, except we don't have separate integer values of your signal in time. You have a whole continuous time signal. Now let's say you have some sort of signal like this, okay? You have a quadratic, inverted quadratic, and your delta function is right here. Okay, so your quadratic is x of t, right? And your quadratic is only going to be alive at x of 0. Why? Because at 0, your delta function is 1, and anywhere else is 0. Okay, so your quadratic is only going to be equal to this point right here. Okay, and if your delta function is shifted by some value t0, your quadratic is only going to be equal to the value of your function at t0. Okay. So that's all. Quadratic was just an example of it. It could be any signal in general. So this is all that this is. Okay. And the next part we're going to talk about is continuous time systems and discrete time systems. This is more important in the second half of the course, but it's just good to get you interested. It started in that because it gives you a different mindset to think about it now that you know what continuous time is and what discrete time is. So you can kind of prepare your brain that you know about these differences. And then when you start systems, you remember, oh, well, yeah, we've seen this a little bit in the past. So all it is your system is kind of like a box that takes an input and gives you an output. And for a continuous time system, the input is a signal of time, continuous time, and your output is a signal of continuous time. Okay. And for the discrete system, you have a box that takes an input and an output. Your input is a discrete time signal, and the output is a discrete time signal. So this is all I have for this lecture. Tomorrow we're gonna move on to other different lectures. Yeah. So again, watching these videos or not watching these videos, yeah, it should help you. But I appreciate you guys watching them. That's the most important part. This would not be possible without y'all. I keep on saying this, but it's very true. That's pretty much it. And the channel's been growing, honestly. 172 subscribers. I think the last time I posted, I was like, what, 165? Honestly, yeah. So if you could give me a subscribe, that would mean the world to me. Thank you very much for your attention and watching these videos.